Hi everyone, let's calculate the Gaussian integral, which is the integral from minus infinity to infinity of e to the power of minus x squared. And since this function is an even function, we can express this integral in terms of half of the distance of this interval, which is from 0 to infinity, but we need to multiply this by 2, and we have the same function here. So for simplicity, let's denote only the integral part as j. So let's say j is equal to the integral from 0 to infinity of e to the power of minus x squared, and we're integrating with respect to x. So the usual method to solve this integral is to if you try to solve this with integration by part or substitution, you will actually increase the complexity of the integrand, and this will lead to nowhere. So we have to come up with a new solution, and that is to square the whole equality. So we get j squared is equal to the integral from 0 to infinity of e to the power of minus x squared dx, and we need to multiply this integral to itself. So the second integral is from 0 to infinity as well, of e to the power of minus. Notice that x is just a dummy variable, right? So I can replace it with another variable. Let's take y. And since both functions are non-negative, and those are actually the same functions, so we can, by Tonelli's theorem, we can try to bring this integral inside the dx integral. So this gives us the integral from 0 to infinity of e to the power of minus x squared times the inner integral from 0 to infinity of e to the power of minus y squared. And the integration order are going to be dy and then dx. So, and since e to the power of minus x squared is a constant with respect to y, we can bring this inside this integral. So this gives us a double integral from 0 to infinity of e to the power of minus x squared minus y squared dy dx. Let's factor out the minus 1 here, so we get minus the parenthesis of x squared plus y squared. So, and mostly one solves this double integral using the polar coordinates, but today we are going to stay in the Cartesian coordinates and solve this with the Laplace method of the Gaussian integral. So therefore we have to introduce a new variable. So we have first to calculate the inner integral. So let's try to substitute y. Let y be, let's introduce a new variable that is s, but this has to be multiplied by x. And now differentiate this gives us dy x times ds. And let's plug that into the double integral. So the outer integral is still from 0 to infinity, and the inner one, you have to calculate the bounds. And since y and x are both greater or equal than 0, then if y equals 0, then this equality is also then s is going to be 0, right? And if y is positive infinity, since x is also positive, so s is also going to be positive. So we have positive infinity, and then we have e to the power of minus, we have x squared plus, now we can substitute for y x times s and square this guy. This gives us x squared times s squared. And we have, for dy, we have x times ds dx. And let's factor out x squared from this parenthesis. So this gives us the integral from 0 to infinity still, e to the power of minus x squared times 1 plus s squared. Let's bring this x to the left side of e. So this gives us, I have to erase this sign a little bit, x times e to this exponent, and we have ds dx. All right, now the inner integral has a really familiar form which one should know, but in order to integrate it, we need to change the order of integration, right? To do so, we need to show that our integral j is going to converge. All right, let's try to show that. Let's try to split our integral as a linear combination that gives us j is equal to, so actually we are going to express this as addition of two integrals. So the first is going to be from 0 to 1 of the same integrand, and the second is going to be from 1 to infinity of the same integrand. All right, let's notice that for all x in the closed interval from 0 to 1, we have that e to the power of minus x squared attains its highest value for x equals 0, right? So this will give us just 1, and any other value between 0 and 1 except 0, this expression is less or equal than 1. And let's take the definite integral of this inequality from 0 to 1. So this gives us the integral from 0 to 1. And here we have the integral from 0 to 1 with respect to x, which just gives us 1. So we found out that the first term is restricted by 1. And the second, we also need to estimate this. We know that on the closed interval from 1 to infinity, that x squared, let me write that here, that x squared is greater or equal than x, right? And if we multiply this by a negative, then we have to flip the inequality sign. So this gives us minus x squared is less or equal to minus x. And we can take these two as the exponent of the same base, right? And let's take the integral from 1 to infinity of both sides. And we know that this integral will give us just 1 over e, or e to the power of minus 1, right? Then we found out that our integral j is less or equal than 1 plus e to the power of minus 1. So therefore, we can change the order of integration of this integral, and we'll do it in the next step. All right, as a summary, we started integrating the Gaussian integral, and we ended up getting the square j, which is equal to this double integral. And by this estimation, we could change the order of integration, and so we have a form that we can calculate. So let's consider the inner integral, which has the form of the integral from 0 to infinity of x times e to the power of minus x squared. And since 1 plus s squared is a constant with respect to x, we can replace it with an a, and we are integrating with respect to x. So since the derivative of x squared is contained in our integrand, so we can replace the whole exponent by, let's say, u. Let u be minus a times x squared. So du is just minus 2 times a times x dx, and dx is going to be minus du over 2a times x. So let's plug that into the integral. So we'll get the inner integral of e to the power of u, and we see that 1 over x will cancel out x, so we can omit that, and we have minus 1 over 2a, which is a constant with respect to u, so we can multiply to our integral 2a, and we have du. And the bounds are going to be if x equals 0. If x equals 0, then we have the lower bound is also going to be 0. And if x equals infinity, then we have infinity squared gives us just infinity, but we have to multiply it with a minus, so we get minus infinity. And this is now a easy integral to calculate. We know that the antiderivative of exponential of e to the power of u is just e to the power of u. So let's calculate it. We have 1 over 2a times e to the power of u evaluated between 0 and minus infinity. If we change the order of the limits, we have to multiply this term by a minus 1, so we get 1 over 2a times e to the power of u evaluated between minus infinity and 0, and this will gives us 1 over 2a times e to the power of 0 minus e to the power of minus infinity. And we know that something raised to the power of 0 gives us 1, and e to the power of minus infinity is just 0. So this will gives us 1 over 2a, and since a is 1 plus s squared, so we get that this is equal to 1 over 1 plus s squared. Actually 2 times this guy, because of the 2 here, and we got that the inner integral gives us 1 over 2 times 1 plus s squared. And let's calculate the outer integral, which is just the integral from 0 to infinity and with respect to s. And since 1 over 2 is a constant, so we can bring this out of the integral. Then we have 1 over 1 plus s squared integrated between 0 and infinity. So this is just the arctan of s. So we have 1 over 2 times arctan of s evaluated between 0 and infinity. And we know as s approaches infinity, then arctan of s is going to be pi over 2. And if s approaches 0, then arctan of s is just 0. So we get that 1 over 2 times pi over 2, which just gives us pi over 4. And this is the result of our integral, which we squared of j, which is here squared. So we get that pi over 4 is equal to j squared. So this will gives us j is equal to the square root of pi over 2. And since we were calculating I, we have expressed I as double of j. So we need to multiply this by 2 in order to get our initial integral. I is equal to square root of pi. Thank you for watching.